Hello, physics students. In this video, I want to take you through some of the basic terminology with standing waves and also how to count standing waves when you are using the equations in the future chapters. Please take your notes out and watch the rest of the video to learn more. Hello, Mr. Standerson here. I want to talk about standing waves, some of the big ideas behind standing waves, how to identify nodes and antinodes, and just some basic general definitions in this short video. So as you can see, the green wave is a combination of both the blue and the orange. Where the blue and the orange constructively interfere, it makes a larger wave, and that becomes a antinode. Where the blue and the orange destructively interfere, that becomes a smaller wave. We call that a node. If I pause this, you can see where the crest and the crest meet together with the blue and the orange wave. It makes a really big green. That's the standing wave that's bouncing back and forth. Remember, these are always in real time, just in interference of all these waves coming together. You can see at the highest amplitude, a crest and a crest meet. And then as it travels through, that crest is going to line more up with a trough. And as we get closer to where a crest and a trough meet up, like in this example, the green wave cancels out completely. This repeated motion, the repeated interference of those two waves causes what we know as a standing wave pattern, where we have nodes and we have antinodes. I want you to please use this idea of a standing wave pattern to talk through some different scenarios. For example, if I wanted to figure out what is the wavelength of the standing wave, I'm going to look from the start of the first node, trace all the way through the first crest, then trough back to where it's a node again, and that's going to become my one wavelength for this standing wave. All right, as I keep going back and forth, I might change the frequency. It's going to increase more standing waves. You're going to explore, does that have an effect on the wave speed? Does it change the amplitude and things of that nature for your standing waves? All right, so you can use this simulation also, but I would also encourage you to use the notes to discover more about standing waves. Please reach out if you have questions. Thanks. Two of the main terms we're going to talk about are nodes and antinodes. So consider a standing wave, and I've drawn this with two different colors to imply that there's two waves that are blending together or more to produce the standing wave pattern that you see. There's a node and an antinode. The nodes are the parts of the wave that appear to be in place. They appear to be standing still in the middle without any amplitude change. Antinodes are the parts of the wave that are the farthest from rest. So these here and these here. Nodes are produced when there's destructive interference produced by the two waves coming together. Antinodes are produced when there's constructive interference. And you can see those places are the highest amplitudes. I want you to now take the idea of nodes and antinodes and consider this wave here. We want to figure out how many waves are pictured in this picture, and we also want to know how many nodes and antinodes there are. That will help us determine wave speed, wavelength, and other calculations down the road. So for the nodes, remember to count any point that is a destructive interference. So we're going to look to all of the places where it zeroes out. So in this case, we have 4 nodes. The the antinodes are the highest points of constructive interference. So in this case, we have 3 points where they have highest constructive interference, therefore 3 antinodes. To find the wave, you want to trace what a full wavelength would look like from start back to start. This is one wave. However, there's more drawn. So there's actually an additional half right here that you can see. So in this picture, there are actually 1.5 waves total. So if we're trying to find out the wave speed or other things and frequency, you want to count with 1.5 waves at that amount of time. They might tell you a distance, in this case maybe 6 meters for one wave, so the wavelength is 6 meters. I want you to be able to use these terms in order to find frequency, period, and wave speed in the future calculations. Please reach out if you have any questions. Thanks.